Okay, differential equations. We have section 3.2. Looking at the top, I can solve logistic growth problems, something that you actually studied in Calculus BC. We're really going to have a different lesson today. We're going to do quite a bit of proof and derivation of some equations. So like I was saying earlier, not your typical differential equations section that you've been seeing so far. But let's just take a look right here. It says the situation of exponential growth, where the population is unbounded, is dp dt is equal to kp, some constant multiplied to the population, which gives the solution P equals C e to the kt. And of course, what we have here is honestly a very famous equation that you would have seen in Algebra 2, where screen jumped just a bit, where you could see that that constant would actually be the initial population. That's not realistic. Sometimes your population won't just be based on that. It has way more factors. Say beta is the birth rate and delta is a death rate. Then that constant that you'd see I should have drawn this right here. This constant that you can think of would actually be beta minus delta. But as we're looking at this, we could see that beta, which would be a birth rate, could be generally thought of as beta naught minus beta 1 times p, a rate plus or minus a rate affected by the population. So as you study populations, you see that the birth rate could actually be written more like so. And the death rate, well, that's just some constant. So, your beta is going to be what we just saw right here, beta naught minus beta 1 times the population minus delta naught times the population. So if we were to distribute, and if we were to do just a little bit of work right here, obviously p times this p, that would be p squared. You get a minus beta 1 p squared right here. If you'd like to save yourself some work, however, get a load of this. This might even be nicer. You could say, well, look at this, beta naught minus delta naught. That's going to each get multiplied by p, or you could just leave it factored out in this regard. That's what we have right here. So this is another way to look at how your population is really changing with respect to time. So what we can do is say, well, wow, look at this constant right here. We could call that A. A is beta naught minus delta naught. And we could say, well, look at this beta 1 over here. We could let beta 1 equal just the letter B. And if that were the case, then very nicely, you could see that you wind up with this equation right here. And of course, we could then factor out a p on this right-hand side. And you can see this is highlighted in green. It is a very, very helpful differential equation that we're going to refer to later, looking at this population growth in that green form. It's going to be very helpful. But tell you what, I'm going to factor out a b. So I'm going to have our dp dt right here. And if I pull out a b on the right, I'll have b times p. Now, of course, this means we're going to divide everything on the inside of the parentheses by b. And when we factor, it's undistributing, so we're actually dividing everything in the parenthesis by a b. By the way, if you're ever wondering if you're right, you could redistribute your b and check it. Well, why am I writing it this way? In Calculus BC, you would have seen the logistic growth written out in this very important form. Textbooks have it all the time. dp dt equals some constant times p, parentheses m minus p, and the m was known as the maximum carrying capacity. But look, we're really saying that that k out in front is little b, and that's super important. And then you can say, well, what about your maximum carrying capacity? Well, your m would be a over b right here. So this is what you did in Calc BC last year. Logistic growth was represented as a differential equation. Well, it's right now where we're going to actually do something that can seem a little bit shocking. We're going to say, you know what? We're going to solve for p. And believe it or not, you did this in Calc BC also. And this is what makes this lesson rather long and drawn out. We're going to get our p's together on this left side. So divide both sides by the p and the m minus p. Only the k does not have a p in it, and we'll multiply by a dt. But remember what m was, and remember what k is also. Your m right here, we could say, well, that's a over b minus p. Well, your k right here is really just a b. So how about we get rid of this b right here? How about we multiply both sides by 1 over b? So I'm going to multiply by 1 over b here on the right. I'm going to multiply by 1 over b here on the left side also. And I'm going to get very creative and say I'm going to distribute this b right here only to this, parenthesis right here. So if we were to look at this left side, and I'm going to bring this over here, this left side, we're going to have dp, and then we'll have a p all over. Well, what's b times 1 times a over b? Well, that's just an a. And then I'm going to say minus. Well, then we'd have bp. So we're going to look at this, and obviously as we're separating variables, you're probably thinking, now wait just a minute. Isn't this really so that we could go ahead and integrate? And then you're probably thinking partial fractions. And yes, that's exactly what we're going to do. I'm going to venture off to the side here with some partial fractions, and very obscure partial fractions at that. My goodness, let's, look at this. We'd have 1 over p, and here's our a minus bp. And I'm going to write capital A. That's what we've usually done right here for our first component. And then capital B all over this little a minus bp. And you might remember what we did is we multiplied everything by that LCD. We did this a lot in Calc BC, and you can quickly see where we're going. The left side, you just get a 1. As you distribute over here, the p's are going to cancel out. You'll have capital A times little a minus bp plus, wow, here it looks a lot nicer. You'll just have a bp. And you can think, well, what should we let capital P equal? Well, I'll tell you what, let's let capital P equal 0. And what's going to happen? You'd have a 1 equals, well, here's your capital A minus, well, B times 0, well, that's going to go away. And we can solve for capital A. Capital A is going to be 1 over little a. And we'd say, okay. Well, then what? We could also go ahead and make another selection for what P could equal. Look, if we're wondering what would be 0, what P value would get us to equal 0, it would be A over B, wouldn't it? So we're going to let P equal A over B. And then what? Well, you have a 1 on this left side. This whole big mess right here is going to cancel out. Because when you have your B over A, I'm sorry, your A over B, your B's canceling, you have A minus A, that's 0. And then over here you'll have your B times A over B. So multiply by your reciprocal, multiply by B over A. And there you have it. Now, please understand that this B right here is really B over A, and this A right here is 1 over A. So this is really like a 1 over A times 1 over P, and this is B over A times this 1 over A minus BP. That's your partial fraction decomposition. So I just wanted to show that to you because, you know, as we're doing this little bit of work right here, as we're integrating, you might have wondered where this came from. Here's that 1 over A, here's that B over A. You know, that's a little bit of a jump right there. And of course, I wrote it with the 1 over A out in front and the B over A out in front. Well, now we're going to go ahead and take an antiderivative. We're going to integrate, right? And, you know, we'll have natural log of P, and we've got our 1 over A here. Here we'll have our natural log of A minus BP, but we have to reverse the chain rule. We're going to actually be very careful. Normally, you'd be multiplying by a negative B if you took a derivative right here from the inside. So you've got to multiply by a negative 1 over B, and you're going to be left with just a negative 1 over A then. On the right side, you take an antiderivative of 1, and you get a t plus a constant. So things are moving along. Next, we're going to use this log property where we can you know, have our 1 over A factored out in front and divide the insides. We'll have our P all over A minus BP. Then we can multiply everything by A. A times a constant is just a constant. We have this right here. And then remember that E is the base of our natural log. So I'm going to exponentiate. We'll have our e to the at plus c. And that's really e to the at times a little constant out in front. By the way, you might think, what about this absolute value? Well, get rid of it. You'll have a plus or a minus that would absorb this constant right here. And super importantly then, you've gotten to a critical step where you can now say, wow, I am closer to solving for P. I hate to say it, we still have to do some work to get P alone. And I'd like to start over here and show some intermittent steps. I'm going to flip the left side, take the reciprocal. And that means I'm also going to flip the right side also. And, you know, as you do that, and of course you could just make it 1 over that whole thing. The reason why we're doing that is so that we can do an I heart math. And over here we could say that's 1 over C1 times e to the negative at. And the p's are going to cancel, and you'll have a over p minus a b is equal to this really e to the negative a over t all over c1. And I'm going to go ahead and add a b over here. And before too long, you're going to say, now wait a minute, couldn't we get a common denominator? So I'm going to multiply the top and the bottom here of my first term by C1. And when you do that, let me get this pen right back. When you do that, you're going to be able to get BC1 plus e to the negative AT all over a C1. Let's make this bigger again. Okay, so that's what we have for our A over P. Our video is going to end, and we'll pick up from here in just a moment.